Hello, we are live. Welcome,
Yeah.
everybody. Thanks for joining our meetup. I will give you a short introduction to the group, and then I will leave the word to Mauro that kindly accepted our invitation. So, our group, our group is called the Ticino Software Craft. So, why Ticino? Ticino is a region in Switzerland. And the people that you see here that are the organizer were working before all in the same company that was lastminute.com that is based in Ticino. So there the group started, so we left this name. Initially, all the meetup were done there, but COVID came and we moved virtually, so everyone can join from all the part of the world. And why software craft? The reason is that we are inspired by the Software Craftsmanship Manifesto. There is a point there that speaks about building a community of professionals, and this is what we are trying to build. So a community in which we would like to raise the bar, because we believe that being average is not good enough. And so we care about the culture of continuous learning. These are our channel. Generally, all the new events are published on Meetup, and then they are spread across Twitter and YouTube, like this one. And that's it. The Q&A, I think, will be we will do the Q&A at the end of the session. And before that, we are going to extract a JetBrains license, so we'll give you the details at the end of the Meetup, at the end of the speech. Okay, so I leave the word to Mauro. Enjoy.
Thanks. Thank you very much. And welcome, everybody. And thanks for having me. That's the most important thing. So tonight we're going to talk about SQS and SNS with an eye as the .NET developer. So we'll try to dive a bit into the API and use that to also talk about how they work, how we should approach them, and specifically, more importantly, what they really are. So let's start with try to understand what's SQS. SQS stands for Simple Queue Service, and we'll see throughout the presentation why simple, right? So what's SQS? It's a queue, nothing more than that. No fancy features, nothing. It's just a queue. What it means that we have a sort of a storage that behaves like a queue. So what comes in first is supposed to come out first. That's not always the case, but we can talk about that later. And then we have a message or some kind of data coming into that queue. And more data will pile up if no one is consuming those data from the queue. And if someone is consuming those data from the queue, they will be picked up and consumed by the consumer of the queue. So that's it, nothing more. So it's simple, but the important stuff is that it's globally scalable, it's extremely reliable, and more important is fast, very fast. And if you combine globally scalable, reliable, and fast, very fast, you can understand the underlying complexity of building something like that. Keeping in mind that the simplicity is probably primarily important for us as users of that thing. And one could argue maybe it's hard to use, right? So let's have a look at what it means using SQS. So we want to send a message. So the first thing we do is create a new send message request. And the only parameters required by this new send message request are the queue URL, where the queue URL is the destination queue URL. Think about the queue URL as a URI that uniquely identifies the destination queue. So it's a string, nothing more. And the body, which could be whatever you want, right? It's just a string. If it was originally a .NET class, it's probably a JSON representation of that .NET class, a serialized class, but can be just a simple text, right? And then what we do is we send the message using the SQS client. And building the SQS client is as simple as doing var SQS client equal new Amazon SQS client. That's it, nothing else. SQS, although, supports a thing called batching, and maybe batching is the complex thing when it comes to dealing with sending messages in SQS. Let's have a look at what it means. So sending a batch is just creating a list of batch entries or send message batch request entry, and then appending one or more of these request entries where we have the entry ID and the body for that ID, for that entry. And then what we do is we create the batch request, and we have again the destination queue URL and the list of entries. And finally, we just send the batch. Instead of doing send message async, it will be send message batch async. Sure, there's some complexities when it comes to batches because we have to split entries by destination. So as you probably noticed by the previous slide, what we have is that the destination queue URL is on the send message batch request. So essentially, all the messages within a batch must go to the same destination. And if we have higher level code that just do a for each loop and then tries to send messages, we want to group them by destination queue. But it's not that complex, though. And the other limitation of batches is that each batch has a limit of 256 kilobytes per batch, which from the .NET developer point of view might be a little bit tricky, because if you're dealing with classes, we have to first serialize those classes, try to understand what's the final size of the serialized message that you want to send, and take into account message attributes, and we'll see them in a minute, and understand, will they fit into a single batch entry, or do I need to have more batches, right? But again, it's not rocket science, so it can be done, right? Maybe consuming messages is more complex than sending messages. Let's see what it means to consume a message, right? It all starts with creating a receive message request. So a receive message request, similarly to a send message request, is a DTO with properties, and it's a little bit more complex than sending a message. So the first thing we want to tell to SQS is how many messages we want to fetch. So that's an important bit. So when fetching messages from SQS, the thing is that there might be 1, 2, 3, 300, 1,000 messages sitting in the queue. We want to tell to the SQS client how many messages in a single batch we want to retrieve for a single request. In this case, it might be 100, whatever. It's up to us to decide how many messages we want to consume in a batch, right? And then what's the input queue URL? So from which queue we want to pick messages. And then it's the wait time in seconds. So wait time seconds is a bit tricky here. So SQS, the SQS client under the hood uses HTTP for every single request to the SQS backend, so to the storage infrastructure, to the queuing infrastructure. It uses a sort of long polling kind of mechanism, and that's the long polling wait time for messages to come in. Let's try to picture what might happen. So we're issuing this receive message request with max number of messages 10. At the time of the request, when it's sent, there are no messages in the input queue. If there are 3 messages, we get 3 messages back. That's it, right? We empty the queue, even if we're asking for 10. We empty the queue and we get what we get. If there are no messages in the input queue, in the queue URL defined in the line above, the SQS client will wait that amount of seconds, so 20 in this case, that is the also default value, for messages to come in before closing the HTTP request and stop waiting for a response. So the second time-related property is what's called visibility timeout. So by default is 30 seconds. The visibility timeout is the time messages will be invisible to other clients, polling the same queue until they are returned to that queue. So in the SQS lingo, they are called in-flight messages. Let's again picture what might happen. So we have 3 messages in the input queue. We go to the input queue with this request. We retrieve 3, because even if the max number of messages was 10, we retrieve 3 of them. And then SQS, from that point on, starts counting 30 seconds. So what it means is that those messages are not deleted from the input queue at retrieval time, right? They are only simply hidden by SQS and left in flight because there's a client instance tried to consume them. If the client takes more than 30 seconds, then messages will be returned, will be made visible again, and another client can consume them. Why that? Because given that the underlying connection is the HTTP, there's no way for SQS to realize that is the client still there, right? So what might happen is that the client picks up a few messages and then the client dies soon after that. So the endpoint crashes, the process crashes, and now SQS will have to make a decision on when shall I resume these messages, and that's the visibility timeout. Visibility timeout is also important from our perspective, consuming messages, because think about the time it takes for you to process those messages, right? It should be shorter. If it's longer than 30 seconds, it's like a transaction timing out, essentially. So messages will become visible again. And if you think about in your head to what a message pump mechanism will be, there's a for each loop or a while true loop that continuously issues receive message requests. So the first one comes in, retrieves those 3 messages that are in the input queue, mark them as in flight, will start processing them. After 30 seconds, we haven't finished processing them again yet. They will become visible again. Our while loop will pick them up again. So we'll start processing duplicate messages. So it's really important to keep in mind that the visibility timeout might have an impact on the message duplication or that might happen at the endpoint level. Also keep in mind that 30 seconds are like a geological era in IT terms. So if your consuming time is longer than 30 seconds, probably you should not make it longer, but you should try to understand how to split that into multiple steps. And we probably talk about that a little bit later. The next attribute we can set is attribute names. So with the messages that we are retrieving, we can retrieve one or more queuing level attribute for those messages. So in this case, we're telling SQS, hey, SQS, with the messages, please give us back the sent timestamp for each message. So what happens is that when messages are sent, they are timestamped with the send time. And we're asking in this case we want them back. There are plenty of attributes that we can retrieve, and they are available on the AWS documentation to understand more. Message attribute names are specific attributes related to the message, and in this case, we're telling SQS we want them all, right? So if there are message attribute names, give them all and return all the values. And then finally, once we have compiled this DTO request message, we can issue the SQS client receive message async. We get back messages, which is a receive message response, which will have the list of messages returned by the client. At this point, we want to check how many they are, because they might be less than the max number of messages. It might be even 0 because there are no messages, and then decide what to do with those messages, right? And proceed with consuming them. All in all, we cannot really say that it's complex, right? There's nothing really complex. It's just exercising a remote API that is not that different from invoking some sort of remote REST HTTP API. So it's not really rocket science. There's There's nothing to be worried about by dealing with SQS from the developer perspective, writing code. Let's have a look at SNS. And let's start again from what SNS is. SNS stands for Simple Notification Service, and it's a broadcast mechanism. So instead of being a queuing system where we send a message to a specific destination, the main concept for SNS is a topic. And as the name topic means, is the argument we're talking about. It's a topic we're talking about. So in a system, there might be a topic that we can call order accepted that will deal with all the orders that are accepted. We might have a topic that is called order shipped. We might have a topic that is called customers checked out. And you get the picture, right? So to a topic, there might be one or more subscriptions. And whenever we want to send, in this case, we want to say publish a message to a topic, that message will go to the topic and will be duplicated for each of the subscribers. So technically speaking, internally, the topic is not that different from a queue. So we will pile up messages we want to publish to that specific topic. And then the topic, the subscriptions, to be precise, role is to tell to the topic, I'm subscribed to that. So the topic will create a copy of the message for that specific subscription. Usually, those subscriptions are bound to a destination queue. So subscription in SNS can be bound to multiple sort destinations. One can be email, text messages. The most common one, though, is queues. So an SQS queue is the subscriber to a specific topic. So in this picture, those 3 messages will end up in 3 different SQS queues, where someone will issue that receive message request with all the parameters set to specific values and receive 1 or more messages. Again, it's trivially simple, right? But again, it's globally scalable, very reliable, and extremely fast, which are the things that we expect from something provided by a cloud provider, right? And again, let's have a look at the API, right? Maybe, I'm pretty sure you understand that that's not the case, but maybe publishing is hard, right? What publishing means. We have a publish request where instead of having the destination queue URL, we have the destination topic. And then we have and I omitted the URL because it was too long, right? It's a URL again. And the body we want to publish is exactly the same as something that could go to an SQS queue, right? And then we just do SQS client.publish async request. That's it. No rocket science here as well. And that's why they are called simple. They are extremely simple. Their focus is to be reliable, globally scalable, fast, and extremely fast. So the question we should ask ourselves is, why are we here? So if all that is so simple, what's the underlying problem we're trying to solve? Why do we want to use messaging? That's the thing we should be focusing on, because dealing with the infrastructure is simple. Well, it might be more complex than that, and we'll dive into some of the complexities later on, but it's not that more complex than what we saw so far. So we want to really understand what's the underlying reason that should make us go to using messages, and why selecting SQS versus SNS versus other technologies like Event Bridge, for example, I studied, by the way. So let's start with the business requirement. You probably saw this screenshot before. So that's one of the Amazon web pages on the shopping cart. That's the old UI. So when you had something in the shopping cart, which price changed over time, you get a notification like this saying some items in your shopping cart change price, and there's a list of the previous price and the next and the current price. Let's imagine how we could implement something like that. So it's it sounds like a nice scenario for a couple of microservices, right? We have the products microservice composed by the item ID, price, inventory, and maybe tons of other properties. We don't care at the moment. And then we have the shopping cart microservice, where we have a list of item IDs, current price, last price, or previous price, right? So that we can fulfill that screen that we saw before. So when the price changes, the price is changed on the product microservice. So someone comes in and changes that price. At this point, the products microservices is quote unquote forced to ask to all the living shopping cart, do you have this item XYZ currently in your shopping cart? And if that's yes, then what the product microservice will ask is, can you please swap the prices and set the current price to this last value that I just got, right? And we can expand this a little bit by introducing suppliers, and that doesn't really change the picture. So we have an incoming request to say from a specific supplier identified by a supplier ID, we're purchasing that item ID at a different price now, and then percolates down to products and to shopping cart. In the same way, so suppliers will ask the product, are we selling any of this stuff? And product will say yes, or suppliers will say, please update the price. And then product will start the update process with all the shopping carts, right? So in the microservices way, and I'm trolling, right, of doing this, we will probably see something like an incoming external HTTP post to supplier, and then an HTTP query from suppliers to products, and then an HTTP post from supplier to products again to update the price, and a similar query from products to all the shopping carts to retrieve the current shopping carts that are currently hosting that product we're trying to change the price for, and finally an HTTP post from product to shopping cart, right? The bad thing about this kind of design is that we're exposed to the so-called snowball effect. So if something goes badly in the shopping cart during one of those two requests, what happens is that that error, given that it's HTTP and is synchronous, will propagate down to products, and then it will propagate to supplier, which will explode. So at this point, we're presented with a very bad scenario in which something down the line that we are totally unaware of, because we're updating, think about it, we're updating the purchase price of something in the supplier's microservice. Now, that thing is blowing up, maybe for a timeout in responding from one of the shopping carts. That timeout will cause products to timeout the same way, or to throw an HTTP 500, and that HTTP 500 will propagate down to suppliers, and the user in front of the screen touching the price will say, what's happening here? Something blew up, and they have no idea how to fix that, because that user might even not have an idea that the shopping cart exists. So how can messages at this point solve that specific problem? So let's view at how we could design the same thing using messages, right? We have an incoming request to suppliers again, and then suppliers will send a message through a queue, for example, or SNS, because I labeled that as an event changed, right? And that message is for products. The message will come with new price details. So all the data required for products to move on are in the message itself, right? Products will have its business logic saying, am I selling this stuff? Are this stuff available for purchase? Yes, let me update the prices. And once that's done, products will publish another event saying, sell price changed with the new price details. And the similar business logic will happen in shopping cart that will say, okay, now let me scroll through all my shopping carts, and that's a query on a database, essentially, right? It's a select items where item ID equals that thing coming from products, and then update swapping the prices. Easy peasy, right? If something goes badly, what does it happen? If something goes badly, like in the error that we saw in shopping cart before, what happens is that the incoming message is retried. So there is no more propagation of failures to the upstream microservices or to the upstream components. Doesn't really matter if they are microservices or not, right? So in this case, the advantage is that from the architectural perspective, we're isolating what should be an autonomous component, that is a shopping cart, using messages. And we're making so that problems within the boundaries of a specific component won't propagate like the snowball effect that we saw before to other components outside those boundaries. It's a shopping cart problem to try to fix its own issues. Messages can be retried, and if they cannot be retried because they continuously fail, let's imagine there's a bug in the shopping cart code that handles those type of messages, they can be moved to an error queue where someone can take a look, understand what's happening, and once the problem is fixed, they can be moved back to the shopping cart input queue. And what will happen is that prices will be updated eventually. So it's not synchronous anymore, but we want to take advantage of the asynchronous nature of messages to avoid the snowball effect and to really say, do we really care if prices are updated, let's say, synchronously to when the purchase price has been updated in suppliers? Probably no. If it happens 5 minutes later, a couple of minutes later, doesn't really matter, right? Let's take a look at, and all this can be done using just SQS. So those messages can be messages on queues in SQS. Right? Let's have a look at a different business requirement. Continuing with the shopping cart example, let's say that we now want to check out the shopping cart and start purchasing stuff, right? We're now a customer trying to proceed to check out. So we issue a checkout request, and now we are in an interesting situation because checking out requires multiple steps. Think about all the steps that you do on the Amazon.com or .it or whatever website you go to, even booking.com, or you have to input your credit card details, payment options, delivery options, yada, yada, all those kind of details to finally pay and complete the order. So in this case, we're thinking about, for example, the checkout process requires placing the order, charge the money on the credit card, and maybe send the thanks email to the customer, right? There are a couple of interesting facts about those 3 steps. First of all, the order doesn't really matter. So if we charge the money, so if we charge the credit card before effectively placing the order internally, who cares? It's not really a problem, right? Given that we talked about messages and that they will be eventually consistent, right? Sooner or later, the place order will happen. And so we might have taken the money 5 minutes earlier than we knew about the order internally, but we will know about the order sooner or later. So, and sending the thanks email maybe should be done after charging the money, but we can also say, just send the email, right? Thanks for your order. We'll get back to you once, if we have problems with the credit card or once the order is shipped. So that generic email thanking the customer for the order can be sent immediately, regardless of the other 2, right? However, the interesting thing is that those things should be all or nothing, right? We don't really want to have the order placed, but never charge the credit card, or worse, the other way around, right? Charging the credit card and never placing the order, because it means that we will be in a scenario in which we are essentially stealing money from customers, because if we don't place the order, we will never know that there is an order to collect for which collect items and then ship, right? So it sounds like the first requirement makes things simpler, but the second one leads us into a sort of a distributed transaction nightmare, right? Because that all or nothing sounds very transaction kind of thing. And we want to avoid that like plug. for two reasons: because distributed transactions are bad by definition, right? And second, because in the cloud specifically, it's extremely unlikely that a distributed transaction will end up succeeding. And the reason relies on the fact that the distributed transaction relying on having very well stable, fast networks between actors in the distributed transaction, participating in the distributed transaction. The underlying protocol of the DTC, for example, on Windows, relies on TCP being extremely reliable, which is not the case in the cloud. So timeouts are a daily thing. So the more actors will be participating in that distributed transaction, the more likely it is that the distributed transaction will roll back because of a timeout or because of a commit failure at the first phase, and the second phase won't ever happen, right? How can we use messaging to overcome that? Well, one option is to do something like this, right? So we said we have the checkout process that happens, let's say, in the shopping cart microservice. Like, do not hang up too much on the names of the microservices. It's just something to label things instead of saying yellow, green, blue, or whatever. Right? So the checkout process can send a message to sales to place the order, and then can send another message to finance to charge the money. So the message will contain, I don't know, something like credit card details, the amount, and the first message will contain the list of stuff that the customer is trying to buy, for example. And finally, there's marketing, which will receive a message from the checkout process in shopping cart with the please send the thanks email. Sorry. What's the problem here? First of all, it works. Right? It satisfies the first requirement. The order doesn't really matter, because now that we know that queues are eventually consistent, what might happen is that finance receives the message before sales, right? Or the marketing queue is super crowded because there are thousands of messages sitting in the queue because marketing is super slow for some reason at processing messages. So we will place the order, we will charge the money, and it will take an hour for marketing to reach the message related to the order that we placed an hour ago, right? That's fine. Doesn't really matter, right? We said that business-wise, we're fine in having these three things behave totally separately and asynchronously. The problem, though, is that we said all or nothing. Now, let's imagine that something goes badly after sending the place order message. So if you recall the SQS send API, we had two options. One was sending a single message. So think about the C# code you could write in the checkout process as var sales request, new send message request, all the details of the message, await SQS client, send message async sales request. And then other two lines for the finance request and the finance send, other two lines for the marketing request and the marketing send. Now let's imagine that after the first request, the endpoint process crashes. Now we sent the first message, we placed the order, but no one will ever pay for that order, because essentially the second and the third message are lost, right? So we said that we cannot really use distributed transactions. So is batching an option at that point? So we saw that the batching API is, from the coding perspective, gives us the impression that we're going to SQS just once, right? Because we're accumulating requests into that list, and then we're using send message batch async with the entire batch all at once. And the answer is no, unfortunately, because batches are not atomic. So what might happen is that internally, each message in the batch, they can fail independently. And we will get back from that send message batch async, we will get back a response saying, hey, out of the 200 messages in the batch, I failed sending 2 of them. Here are the errors. Now, up to you to decide what to do. But what if we crash before receiving that response, or we crash processing that response? So the problem is that we will never send some of the messages, right? So one possible solution is to use a thing called the outbox, right? The outbox is not an AWS thing, is not an SQS thing, is not an SNS thing. It's just a pattern to solve that specific problem. We'll talk about the outbox a little bit later, because the outbox is useful, but in this specific case, there's a much simpler solution, right? And we can use events to achieve the same problem, to achieve the same solution, right? Solve the same problem. What we could be doing is that shopping cart publishes a check it out event to an SNS topic. So it's a single operation going to a single resource, the SNS topic. On that topic, there will be 3 subscriptions. Each one of them will receive, in an eventually consistent manner, a copy of the check it out message published originally by shopping cart on the topic. The interesting thing is that obviously SNS could be failing in dispatching to one of the subscriptions, but SNS has retry policies. As we saw before when we were retrying the incoming message to shopping cart, when there was the failure in the snowball effect sample, right? We were retrying the incoming message on the shopping cart. SNS has the concept of, I will retry for a certain amount of time, backing off. So it means that the first retry will be immediate. The second retry can be 5 seconds later, and then 10 seconds later, and then a minute later, whatever. And if something goes so badly that I continuously fail to deliver to one of the subscriptions, to one or more subscriptions, first of all, I can drop a message on CloudWatch. So it will be logged what happened. So there is a trace that we lost something. Or even better, there is this concept of poison queues. So there could be an SQS queue where SNS will direct the failing message, and then again, we can have a look, understand what happened, and retry the message, right? Fix the problem and retry the message. There might be an outage in the AWS data center we're talking to, and we can fix that if that's the problem. So in this case, what we're doing is that instead of dealing with multiple send requests that cannot live in the same transaction within the checkout process, we will just send one single message to an SNS topic, and it's the responsibility of the topic to duplicate that message to all the subscribers. And now we fulfilled both requirements, right? The order doesn't matter because from the receiver perspective, they will receive that check it out message into their input queue like it was before, and they will eventually receive. So we don't know about the order, but now we are pretty sure that they will be delivered sooner or later. And there is no chance that our process will crash with a partial delivery kind of scenario, which is the worst nightmare in a distributed system, right? So before diving into a little bit more topic during the recap, let's answer a question. What about event bridge then? So SQS and SNS are the foundation of the messaging related services in AWS, right? Event bridge is a sort of SNS kind of competitor. So if you look at the documentation, they seem to be doing sort of the same thing, right? If you dive into the characteristics of both, you will realize that SNS is way faster than Event Bridge, although Event Bridge is more reliable than SNS. And Event Bridge has the concept of transformers, which doesn't exist in SNS. So SNS is a pure, extremely simple broadcasting mechanism, right? If you have to integrate different systems, that you don't really own, so for which, for example, you cannot really code something, and the source and destination system have a hard time talking to each other because of the message format, for example, Event Bridge is the solution. That's the bridge in the name, right? So what you can do is having code in Event Bridge that handles the incoming message, transform that, and then sends the message, transform the message to destination. It's essentially a sort of a message broker, very similar in some sense to stuff like MuleSoft or what was Beanstalk from Microsoft, right? Or there's one from IBM, I think it's called Typical, that does the same thing. So those kind of things where you can have power users coding stuff in the broker to handle and to transform incoming messages and adapt them to the destination source. Right? In fact, in AWS, there are tons of adapters to connect existing AWS services and their events to destinations. So let's imagine that you're building a monitoring system. Well, there is already a monitoring system in AWS for your services. Let's imagine that there isn't a monitoring system for AWS services, right? So you have to build your own. You can use Event Bridge to say, okay, I want to listen to all the events coming from Lambdas. I want to listen to all the events coming from SNS. I want to listen to all the events coming from S3. And you can use Event Bridge to essentially funnel them into a single destination that is your monitoring solution, and receive those messages in the same format with the same kind of information, normalized, and all that kind of stuff in order to be able to understand, okay, what is my system doing, right? That is different from what we talked about so far, that is how my system communicates from the business perspective. In that regards, given that we have full control over the sender and the destination, in theory, we're supposed to have, then SQS and SNS are a better fit for that specific thing, right? So, a not so quick recap. So, first of all, why do we want to use SQS? So the goal of SQS is to send, to fulfill the one-to-one communication requirement, or we're talking about commands. So let's imagine, we'll have to introduce a bit of architectural concept here. So when talking about messaging, messages are the foundation of two things, commands and events, right? When we're using, they are both messages, right? From the infrastructure perspective, they are exactly the same thing. It's a string that has a meaning for the sender and the receiver. That's it, nothing else. SQS and SNS, they don't care what we send, right? So architecturally speaking, a command is the sender saying to the receiver, do this for me, right? So we're sending a command to a specific destination or to one or more destinations because we're talking to multiple receivers and we wanted them all to do the same thing, right? Or start processing the report, check out the order. Those are commands, right? The main characteristics of commands, the main attribute of commands is that they are one-to-one. So SQS is the perfect fit to send commands. We're sending a command to a destination queue. SNS is, on the other hand, designed to one-to-many communication or using events, right? Architecturally speaking, an event represents something that happened in the past and is immutable. The customer checked it out. There is no way back, right? We can cancel the order, but we cannot really undo the checkout. The customer can, in reality, but because it can go back to the previous page, right? But the fact that it checked out once or twice or three times, it's a fact that happened, right? So the shopping cart process in our sample will publish that event saying, hey folks, the user checked it out. Is there anyone interested? No, I don't care. The user checked it out anyway, right? So I'm publishing that event anyway. there are thousands of subscribers, fine. I don't care either because I don't know them. I just publish the event to the topic. So SNS is specifically designed, and Event Bridge will do the same thing. But we saw that is really designed to do something else. But under the hood, we'll solve the same problem. SNS is specifically designed to say, give me one event or one message, and then I will broadcast that to all the subscribers that I know now. So there might be a subscriber coming later. That subscriber won't receive a message published before he became a subscriber. And that's fine if you think about it from the business perspective. So most of the times, or I'd say 99% of the time, you don't care about the past. There are scenarios in which you want to rebuild the past, but that's a completely different story. And we should not be using SNS for that. That's not what SNS is designed for. SNS is for one-to-many communication, real-time, quote-unquote, live communication. So what happened now will be consumed by current subscribers, right? Then we want to be very careful and use the outbox pattern that is meant to help in coordinating locally different operations. Let me try to give you an example. So let's imagine that you have an incoming message that is place the order, right? Placing the order requires talking to the database to store some stuff and then publishing an event, order placed, right? Now, remember that we don't have distributed transactions, right? So we have now 3 operations: an incoming message for which we have a visibility timeout. So we picked up the message from the input queue, and the visibility timeout is 30 seconds, right? We're essentially handling that message with the left hand. Now we start talking to the database, and with the database, we can open a transaction. Even if it was DynamoDB, we can have a transactional session with DynamoDB, right? So we can start talking to the database in a transactional manner. If something goes badly, an exception will be thrown by the database, and we will release our left hand, and the message will be visible again. Fine, we're happy with that. Now, we want to also send one or more messages, right? Maybe we want to publish an event, send another message. So now we're back in that scenario in which we have to, we have to send 2 messages and publish an event. We cannot really have one single event like we had before. And even if we could, we still have the transaction with the database. So all these 3 things, conceptually, must be in the same transaction, but we cannot have a transaction. How can we solve the problem? So the outbox is the act of saying, okay, let me be smart, and instead of sending messages, I'll store messages in the database. So instead of sending messages, I'll go to the database in the same transaction with the data and store there message send intent, right? So there will be an intent to send a message, an intent to send another message, an intent to publish an event. And then there's a background process that looks at that table with intents, continuously look at that. And when there is a new intent, it will pick it up from the queue and from the table, that at that point will be similarly to a queue, and will do the thing, like publish the event, send the message, and then mark the operation as done. Do not delete the operation, but mark the operation as done, right? Obviously, what might go wrong is that we succeed in sending the message, but we fail in marking the operation as done. Oops, now we have a problem, right? If at that point the process crashes, now we have a leftover in the database because we sent the message, but that message is not marked as sent. When the process will start up again, that background stuff will check messages and will send the same message again. Fine, that's not a problem because the outbox pattern is both an outbox and inbox pattern. So at the receiver end, what we could have is that when the receiver receives a message, messages are identified by a unique identifier. So the receiver will receive a message, we look in the database and say, have I already processed this? Is there that ID in my database already? If it's a no, it will add it and start processing the message. If it's a yes, it will just discard the message. So when we have this outbox pattern in all the endpoints in the system, and we must have the outbox pattern in all the endpoints in the system, what we will end up with is that in the worst case, there will be more messages traveling in the system, but endpoints will process messages exactly once. So it's not exactly once delivery, like if there were transactions, but it will be exactly once processing. Unfortunately, there are corner cases. So we have to think about retry patterns and idempotency. Why? Think about charging the credit card. We're dealing with a remote API. So we're maybe calling the American Express API, and we might be unlucky, and the remote API we're talking to is not idempotent. So we cannot really call that multiple times, right? So can we retry a failing incoming message? Not really at that point, because we might end up charging the credit card more than once. So whenever we're leaving the boundaries of our system, we have to think about how are we interacting with the remote thing. Can we call that thing, assuming that we call that always in the same way, continuously without side effects? So will that thing be idempotent? If it's a yes, okay, right? Let's do it. If it's a no, we might be in a very bad situation. Imagine that we call the remote credit card API. That credit card call succeeds, but what times out is the response. Now we are in an extremely bad situation in which we have a failure and we have no idea what happened on the other side. So we cannot really retry that. So for example, in this corner case, what we should be doing is that the so-called payment gateway is a single process, and it becomes a single point of failure in the system. But that's fine. That's why we're using messages, and we'll get to that in a second. And that process, being a single process, is configured to never retry a message. But instead, a failing message will be immediately sent to the error queue, because we want to have a human coming in and say, okay, what happened here? Let me pick up the phone and call the credit card provider and understand, did you get this? Or was it a mistake on our end? Because if it was an error on our end, we will retry the message. Otherwise, we're fine, right? We will just fake the processing response. So obviously, from the code that we saw so far, it's clear that we need more stuff. So the code that we saw so far is a very simple way of interacting with simple services. But if you start thinking about a complex system, there's a very high chance that you'll end up writing more infrastructure code than business code. That's not what you want, right? So you have to start thinking about routing. Okay, where are my endpoints? Can I hard code in the code those destination URLs? No, because otherwise you'll start having spatial coupling. Right? You cannot move endpoints anymore or change their input queue names, and you'll be screwed because all senders will start failing in sending messages. And then you'll have to start coding first and second level retries. So for example, you have an incoming message, that message processing fails. Shall it go immediately to the error queue? In the credit card example that we had just before, yes. In all the other examples, maybe no, because that might be a transient failure. So let's imagine that we're talking to a database and there's a deadlock in the database. We might want to retry that message in a tight loop a few times, maybe 5, and then we want to delay the message for 5 seconds and then try again 5 times, and then 10 seconds, then try again 5 times, and so on for a while before moving it to the error queue. SQS doesn't provide that out of the box. So you have to start coding it yourself and start to think about, okay, how do I delay a message? How do I delay a message in the safest possible way without using transactions? There's a lot of complexity, accidental complexity kicking in that you don't want in your business code, right? And then you have to start thinking about serialization. can I have multiple serialization formats in the system? What if I need to change the serialization format over time and moving, for example, from XAML to JSON or protobuf, or have multiple serialization formats in the system because we're dealing with a part of the system that is legacy coming from the past and we cannot touch that, and we're building the new one on JSON, right? And then, as I said, we need to code the outbox, and a similar thing to the outbox, which I'm not going to dive in, which is called the transactional session. So in the outbox sample, we said we have an incoming message that is checked by the inbox, and then we're dealing with the database and, for example, outgoing messages. In the case of a transactional session, it's a very similar concept to the outbox, but instead of having an incoming message for which we have the inbox to check, we have an incoming HTTP request for which we have nothing to check, right? Because an incoming HTTP request we cannot really have requirements like, oh, you must have an ID on the request that is unique, right? So the transactional session is a concept very similar to the outbox for this second specific tenant scenario. And then we have to deal with distributed sagas and workflows. So the two samples that we saw didn't require any coordination across endpoints or microservices or components in the system. But in real life, we have to coordinate in somehow or orchestrate somehow all these components, right? How do we do that? How do we code that? Is what AWS provide, for example, step functions enough for the coordination needs and orchestration needs that we have or not? That's why there are messaging frameworks. These are the four that I know of in the .NET space. I work for the third one. And recently, the AWS folks start discussing building their own native framework to simplify people's life when dealing with SQS, SNS, and other AWS services. And that's very welcome, because when you start coding against those APIs, you realize, oh, that's awful, right? Who designed the SNS API isn't the same group of people that designed the SQS API, and they are designed in slightly different ways. And it's not always easy to understand, what should I do here? Because that's not the same behavior that I saw before, right? So it's very welcome that they're thinking about consolidating all those APIs in a more cohesive kind of framework. I'm done. Slides are available at that URL. So if you want to download them, they're already there. And I'd like to thank you very much and open the floor for questions.
Thank you. It was very nice. Very nice.
Thanks.
Thank you. Yeah.
So we promised the JetBrains license. So
Ooh.
the first one that will send me a message on LinkedIn will win the license. I'm gonna put also my LinkedIn page in the comment. And unless it's Paolo, if it's Paolo, we will ignore the first DM.
Yeah.
I saw Paolo connect. And that's it. And then I think we can see the question.
Oh.
I was pretty sure there was someone coming with something else that I didn't know anything about. I don't know. I'll have a look at what Kinesis is and write a blog post about it. I'm not sure what Kinesis is. So there are plenty of AWS services in the messaging space. So for example, one of the things that when it comes to queues and topics, one of the things that AWS support is ActiveMQ. And you can set up the service using the ActiveMQ API or the RabbitMQ API. Mm-hmm. So it's the same service that exposes two different APIs. And it's essentially a consolidation of SQS and SNS. Why does it exist? Primarily for migration purposes. It's a way to allow people to say, I have an on-prem service system using RabbitMQ. I want to migrate to the cloud. shall I manage the RabbitMQ cluster? No, thank you, no. And so ActiveMQ with the RabbitMQ API. And given that Paolo says also that it's like Kafka, more or less, then it's a streaming service, which is a different thing from messaging. So in theory, we could use streaming services like Kafka for messaging purposes. The main difference is that when a message is consumed from an input queue, it disappears from the queue. And that's exactly what we want. When we're consuming a stream, we want to keep the messages, the events, because that's a better name, in the event log, and have a cursor telling us where I am, right? Paolo might be at a different point in consuming the string. I'm at a different point. What's different from the coding perspective? So the main difference is that in a streaming scenario, we are responsible to keep track of where we are, because if we crash and we start up again, we will be at the end of the stream. And then we'll have to start consuming messages again. If we already consumed 1,000 of them, then we have to start again, right? And remember that we already saw that 1,000, right? So move the cursor to the 1,001. The side effect of that, if you think about it, is that we will lose the competing consumer concept that queues provide. So what the competing consumer is, we can have a single input queue and multiple processes consuming message from the same input queue. And thanks to the visibility timeout, those messages will be consumed only once. And that's exactly what we want. Exactly. So we don't want the duplicate processing, right? So we have an incoming message that is place order. And maybe we have 1,000 incoming messages place order because we have a large system, right? We have 10 different sales processors. So sales processes processing those messages. The first one will pick, let's say that if you remember that API at the beginning, the request message, the request message DTO, we had a number of messages to pick. Let's say one for the sake of the sample. One, visibility timeout, 30 seconds. So if we have 5 endpoints, the first endpoint will pick up one message. The second endpoint will pick up the second, because the first is in flight, so is hidden for everyone by the first one, right? The third will pick up the third message, the fourth and the fifth. And now we have 5 different messages we're processing at a time. Or if we're picking up 100 messages at a time, we have 500 messages processed at a time. If they all succeed, they will be all deleted from the input queue. And that's exactly what we want. If someone fails, that message will be made visible again and can be processed by someone else. If we have the same competing consumers it's a topic again, on a streaming service like Kafka, then given that events are not deleted from the stream, we cannot really have competing consumers because they will consume the same message again and again and again, unless they find a way to talk to each other saying, hey, I'm picking up number 1, I'm picking up number 2, I'm picking up number 3. And so they start skipping. But this coordination has a very high cost. So depending on what you need to do, a streaming service might be the solution. And a different service, SNS, might be a better solution. True, you can have partitions in Kafka to partially solve that problem, but a consumer to a partition is a single consumer.
Yeah.
So if that crashes, it's gone, right? And repartitioning those stuff is not really easy. So it's there's another interesting one. Before going to the Ogden, I think, hopefully. So you mentioned Poison Queue for unsuccessful delivery of messages. Is this the same? Yes, it's exactly the same thing as dead letter queues. Every single system calls them in a different way. So for RabbitMQ, I think they're called Poison Queues. They're probably called dead letter queues in SQS and SNS. and they are called poison queues on Azure, so if I recall, on Azure Service Bus, if I recall correctly. But they're essentially the same thing. So the difference might be this. In Azure Service Bus, you have a poison queue. Let's call them poison queues in general, right? You have a poison queue per queue. So every single queue can have a poison queue, and then you can have forwarding logic to move all those messages to a central poison queue, because you want to look at possibly at one poison queue. In AWS, you can configure a central poison queue or have a sort of cluster of poison queues, depending on, maybe you have 5 teams and you can have 5 different poison queues, and each one is handled by a team. In RabbitMQ, you can have multiple poison queues and forwarding logic to mix up messages in poison queues automatically to end up in a specific destination. Last one from Paolo is that's a bad thing. So, so message ordering doesn't exist. Well, they sell it, but it doesn't exist. So FIFO queues are a thing, right? They are both a thing in SQS, and they are a thing in Azure Service Bus. The Azure Service Bus FIFO queue thing is not really a FIFO queue. It behaves in a slightly different way. So a FIFO queue in SQS is a proper FIFO queue. So it's first in, first out, right? Fine. We're happy with that. The problem is that the only way to make sure that you consume messages respecting the order is to have single process, single threaded consumer. Because otherwise, as soon as you have multiple threads consuming from that queue, your order is done. If you have multiple processors, so multiple endpoints processing from that queue in a consuming, in a competing consumer concept, that order is gone. So my suggestion is always to do not rely on ordering. When designing distributed systems, order should not exist. And even if it was possible to guarantee ordering somehow, then you have the problem of failed messages. Let's imagine that you have 10 messages in the input queue. You pick up the first, done, fine, we're done. The second, done. The third, it fails. It goes to the error queue. Now, what about the fourth? What do we do? Do we discard it? Do we stop processing? Can we process it? No, because if we rely on ordering, now we're missing one, right? So we are in the same problem, the same situation as TCP, where we're losing a packet. So we can request the same packet to the sender. We cannot do that with messages. Otherwise, we have to discard the entire communication flow and fail, right? There are better ways in distributed system to handle that. And depending on the process, is to move that logic into the business logic. And so let me give an example. Let's say that you have an order processing mechanism where you're trying to sell stuff, something similar that we just saw. And you have a fourth actor in the system that is shipping, right? Shipping, in order to be able to ship, needs to receive an event from sales saying order placed, and an event from finance saying credit card charged, because otherwise we don't want to ship, right? It's very easy at the beginning of designing distributed systems to assume that, well, the order will be placed for sure before charging the credit card. And so it's very easy to code shipping so that the shipping assumes that the order placed message will come in before the credit card charged message. And that's a problem, because we know when using queues that that's not the case at all, right? So it might happen that the credit card charged message will come in before the order placed. So what we want to do in that case is to design a very simple saga, it's conceptually called. So imagine having something that you can store in the database where you say, I received the credit card charged message for order number 123. Okay, fine. I'm happy with that. I'm shipping, I'm doing nothing because I never saw the order placed event. When I will receive the order placed, I will check, have I already received the credit card charged? Yes, I can proceed. No, I will wait. Right? So the shipping will become a sort of coordinator across multiple messages, right? Saying, I'm buffering them, storing the information that I received them, and when I have them all, I can proceed with my job. The important bit at this point is that shipping needs to set up a thing that in the distributed system world is called a timeout, to say, when will I stop waiting? Is that so? Okay, I received the credit card charge. I expect to receive the order placed event within 12 hours. If that doesn't happen, given that everything is asynchronous and the original user placing the order is not in front of the screen anymore, I shipping need to do something. So setting up a timeout is essentially sending a delayed message to ourselves. So shipping will send a message using the queuing system, saying to the queuing system, hey, I want to send this message to my input queue, so to myself, but not now, but in 12 hours. That cannot really be done with SQS because SQS FIFO queues, in that regard, they support a maximum of 15 minutes delay. So now we have to start thinking about, okay, how do we do that? So for example, CloudWatch events and cron jobs are a solution. So what we can do is to go to CloudWatch and say, hey, can you set up this cron job? And when the cron job expires, take this payload and put that payload in my input queue. At that point, we have the delayed message, right? So I will receive a message. I don't care where that message comes from, but I will receive a message within 12 hours that tells me, have you received the order placed? No. Now I will do something else, right? Maybe I escalate that to the operations team in order to try to understand what's happening. Okay. Who's asking all these difficult questions? Okay. Okay, so before that, shouldn't you try to add the messages to a saga for ordering? That's exactly the thing that we discussed. So the thing that we discussed is what a saga is, essentially. So what is your approach in testing these kind of systems? It's a sort of a shit show. So first of all, there are two types of testing strategies. Two types of testing strategies. One is, say, what am I testing? Am I testing the business logic of single components? So let's imagine I want to test that charging the credit card works. So I have a component that receives a trigger, which is a message, fine, and then exercises a remote API. I can mock that remote API, and I can fake the incoming message. All that can be a unit test that runs in memory. I'm happy with that. If that thing requires a database, then it can be mocked, it can be a live database, whatever, but it's still a unit test, right? So that's the simple part. The complex part is that if you want to test, let's call it the choreography of different autonomous components in the system to make sure that, yeah, but I want to test my business process. I want to test that when the user presses the checkout button on the web page, everything happens in the way I expect it to happen. And maybe I want to be able to inject failure scenarios into the test, saying, okay, what happens if this thing blows up, right? Or it starts failing, or it starts sending malformed messages? Is my system resilient, right? In that case, it's extremely complex. There is no one solution. So the easiest and thing to do, and as I'll describe the easiest thing to do, you'll probably start screaming, is to make sure that your endpoints could be deployed as containers.
Okay.
Right? That's one thing. once you're able to automatically deploy your endpoints as containers, you have to be able to have sidecar containers being able to pilot those endpoints. So those endpoints should be able to expose a sort of piloting API that allows you to tell to the endpoint, hey, a user is checking out, even if it's not true, right? There is no button click, but there is sort of someone faking that post, HTTP post, right? At which point, the endpoint will behave like if it was in production. So we'll try to go to the queue, deliver a message, go to SNS, publish an event, whatever. Right? All the other Docker containers will behave like if they were in production and start picking up messages.
Mm-hmm.
The problem now is that you want to be able to have sidecar containers for each of these production-ready sort of containers that are able to talk to the production-ready container and asking, have you received the message? What have you received? What have you done? What kind of error have you produced? Because you want to be able to report back to the test, you're failing, or here are the errors, right? So now, if you wanted all these to be automated tests, now imagine the code you have to write. You're writing a unit test, technically speaking. So it's a method in a class, and that method in a class must be able to compile Docker images, kick off Docker images, wait for that thing to be deployed, kick off sidecar containers, exercise the sidecar containers, wait for an asynchronous thing to complete, monitor poison queues, and finally make a decision, green, red, right? Okay, good luck with that. I'm sorry.
Yeah, it's quite hard with these strategy.
It's extremely complex. One of the things I'm working on the side is small is an open source framework that does all what I described, but I'm banging my head against the wall because it's a nightmare, because obviously the framework knows nothing about your code. So it's extremely hard to make that very generic so that you can just code against something like NUnit, right, or XUnit. It's not that simple, unfortunately. So books. And okay, before going to books, go to the last one. The testing infrastructure is kind of more complicated than the actual infrastructure. So there's another one from Paolo, the last one.
This?
Yes. So, no, sorry, no. The last one.
This.
That one. The testing, Paolo is right. So with this, Paolo is onto something. And I didn't want to enter into this sort of moving sense kind of territory. So a good addition to Paolo's comment is testing production. So that's why many companies doing proper distributed systems, they forget about this kind of infrastructure testing. They do unit testing to validate that single components behave the way they expect, and then they do all the rest of the testing production. Think about what might go wrong. So you deploy a new component that behaves correctly in isolation, but when inside the system misbehaves for something, right? Now, what's the worst thing that can happen? That a message will end up in the error queue. Who cares? The system is already designed to be eventually consistent. So someone who will look at the error queue will understand what the problem was, fix the bug, write a unit test to validate the bug, redeploy the component, replay the failed messages. And we're back online as we were before. Obviously, it's easier to say than to do, right? But that's the mindset we should aim for in the long term. I won't suggest this as the first thing, right? Let's start and deploy to production blindly and do whatever we wanted, because we will fix that. No, that's not the case. But that should be the thing we are aiming at in the long term. That is, it costs so much to do infrastructure testing, or as I call it, end-to-end testing, that is not worth it. But it's easier to deploy in production and solve the problem in production if it fails. because we have unit testing covering the autonomous components business logic. And the problem here highlights something else that is worth briefly discussing. Whenever I talk about components, I usually use the word autonomous components. So the attribute is they must be autonomous. So autonomous components means that if a component, in order to fulfill its business requirements, needs another component, that's not autonomous anymore. They are coupled, and they are a distributed monolith. So, and at that point, we must be able to do end-to-end testing, and that's a problem, right? So we want to make sure that we design autonomous components so that that first unit testing approach I described tests, let's say, 95% of the component surface in the system, and we leave just at 5% or even less for the production testing, where that production testing is probably some, I don't know, Q&A environment, right? Where you drop the component and have a bunch of people trying to destroy the system. And it's not a real production system. And if it goes through that environment safely, it will end up in production, to which is exposed to tons of people. Competing consumers, and we're going slowly into more complex territory, allows to have another very interesting thing, that we can have different versions of the same component running in production at the same time. So if messages are always backward compatible, and the events should be backward compatible, because events are a responsibility of the publisher. So I, as a consumer, cannot really demand the publisher to say, hey, can you give me some more information in that message because I need more? No. The publisher decides what goes into the message, right? It's an event, it happened, here are the information you have. Now, I can have two processes, one V1 and one V2 or V1.1 of the same component as competing consumers consuming from the same input queue. If something goes badly, let's imagine that 50% of the messages will end up in the error queue. But if we have 10 endpoints as competing consumers, then we deploy 10% of the messages are subject to, in theory, right? 10%. And it's a kind of deployment.
Yeah.
So we'll try it. If it succeeds, then we'll go on adding more instances of V1.1.
Interesting.
Where the complexity lies is that there are scenarios in which guaranteeing messages backward compatibility is not that easy. So those things need to be handled with care.
Yeah.
But it can be done. So otherwise, companies like Netflix won't exist.
Yeah, it's very interesting.
Oh, there's a very interesting one. How can we handle sensitive data in messages? So by encrypting messages information, properties, or the entire message. So there are three things that can be done. Let's imagine that we want to send the credit card over a message, right? So we can encrypt the credit card number on the message. So the thing that we need to have is that both receiver and sender, they share the same encryption key or the same certificate that will be used to encrypt and decrypt the message. We can encrypt the entire message, right? That's not a problem, because from the transport perspective, so SQS or SNS, what goes into the account doesn't really matter. Or so what's the why don't always encrypt the entire message? Because the problem might be that if the message ends up in the error queue, it will be ununderstandable by anyone that tries to understand what was this about, right?
Yeah.
Instead, if we have a JSON payload where we have credit card number and then a series of hearts and squares and rainbows and whatever, right? That's fine. It's credit card. So this, I know what that message is, and I don't care about the credit card number, right? But I care maybe about the message structure, and there's a missing property on this message because we updated the system and that was an old version of the message, right? Whatever. A third option, if we need to avoid tampering, but we don't care that much about sensitive data, is just to sign messages. So we can essentially calculate the message CRC, sign that, and then ship the same value to the destination. The destination will apply the same signing algorithm and checks the signature. So we know that the message has not been tampered along the way. All these obviously assume that an attacker doesn't get control over the machines where the processes are, because otherwise we're screwed anyway. So that's not the problem we're trying to solve.
Okay.
Hopefully I answered them all. Hopefully. Otherwise, people could reach out to me over Twitter and ask more questions. I have no problems.
Maybe the book we skipped.
I have no idea. I have no idea. Okay, so I don't know about the book. There's we have as a company, we have a learning course that is for free, that is called Advanced Distributed System Design Fundamentals. And it's something like 30 hours, 25 hours of video materials discussing all the topics that we discussed today. And then there's also a paid option that is way much longer, but it's a paid option, so we don't care about that at the moment. The book, the Sam Neumann one about microservices seems to be a good one. I'm not really a fan of the microservices theory. So the microservices theory comes with a limitation, in my opinion. That is, it conflates the logical nature of services and the physical nature of services. And the word micro is the worst thing that could have been prefixed there. So the problem with micro is that it focuses on the size, which should not be a problem. And what micro means is problematic to me. Because is it 5 lines of code micro, or 50 lines of code, or 500 lines of code? We don't know. Sorry. But let that aside for a second. One of the important things when talking about distributed systems is distinguishing between logical components and physical deployment of those components. Let me give you an example again. So let's imagine that we have a security service. It's an overloaded term, but that's fine for now, right? So the security service is responsible for 3 things: authorizing users, authenticating users, managing users. Right? Managing users is clearly a service on its own, right? Because we have a database of users, we have a user interface to manage users, create, assign groups, blah, 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 whatever we do usually when we manage users, right? And then we have authorization and authentication that should happen somewhere else, right? So is that coupling? Not really, because what we could be doing is that security deploys a component that is physically hosted by an ASP.NET application, and that component is a request delegate that hooks into the MVC request pipeline, checks the bearer token, and blows up if the user is not authenticated, or redirect the user to the authentication web page. And the service, the logical service that is deployed in the same HTTP API knows nothing about the component. So they are physically deployed in the same place, but they are logically 2 separated things, right? So this distinction disappears in the microservices theory. And that leads to, if we don't pay attention to this distinction, it might lead to weird designs where we end up in need of sharing data across services that should not share anything. And that creates all sorts of issues down the line. But we will realize those issues too late. And I have a talk that specifically discuss that. So I want to go into a 90 minutes thing about those things. So there are plenty of bad things that can happen at that point in a distributed system. Right? If we really want to design a proper distributed system, we will be very careful in not sharing anything. That's why Sam Neumann book is a good book, but it's too focused, in my opinion, on microservices. In the end, Sam Neumann invented them. So that's fine. So, and we want to be careful in picking out other books. I have no idea.
I put the course you suggested in the comments, so there is
okay. Thank you. Thanks. So there's there's another one. Observability isn't a very good one. So there are a couple of things that we should be observing. Okay, so first of all, how should we observe? The best approach nowadays for .NET people is OpenTelemetry. So now the .NET framework, .NET, because the .NET framework is something else. So starting .NET 6, OpenTelemetry is fully supported, and all the frameworks I talked about before. So for example, NServiceBus will support OpenTelemetry in the next major release. What it means is that all those things, so SQL Server and the SQL client support OpenTelemetry. The Amazon SQS client will soon support OpenTelemetry. All those things can produce data in a standard format that can be shipped to something. And that something is an OpenTelemetry receiver that is then capable of graphing out, saying, okay, here is some data about your system. What shall we be looking at is a different story. When talking about queues, we want to be looking probably at 4 key metrics. That is number of messages waiting to be consumed in the queue, so the queue backup. How many messages are sitting there waiting to be consumed? If they are stable, usually that's not a big deal. It means that there might have been a spike in the delivery, but we're consuming messages at a stable pace, and sooner or later we'll catch up. If they are increasing, it means that the resources on the consumers are too low. And then we want to understand why are they increasing. And the second metric we should be looking at is the number of retries. So how many times are we retrying a message? Because that might be a sign of a dependency of the endpoint processing messages is failing too much and is causing all those transient failures causing retries. And then the third metric we want to look at is the message processing time. So how long it's taking for the business logic to process the message. So for example, when it comes to SQS, if it is very near to 30 seconds, then we might soon face a problem, right? And we want to have a look at that. And the fourth one, I never remember, it's called critical time. And it's the time it takes from when a message is sent to when a message is successfully processed. So it's the processing time plus the time in the queue, right? And that's important for SLAs. So we might have a service level agreement with customers or internally saying we want to be able to complete the processing of an order within a minute, right? Why is it taking longer? We're going to look at those numbers and try to, there it is. It's sitting in the queue for too long. So message processing is fine. It's taking 2 seconds, but then we have a backup in the input queue of 10,000 messages. So the message is sitting there for 9 minutes. That's unacceptable. So based on those basic numbers, we can understand what's going on and where to pinpoint and fix problems.
Okay.
Perfect. I think we answered 30 minutes and more of question. Thank you.
Hopefully you're not more scared than what you were before.
Perfect. Thank you. And see you in the next meetup.
Thank you very much, Mauro.
More than welcome. Thank you very much. Thank you very much.
Bye-bye.
Bye-bye.
Bye-bye.